Hello. This work was done by Kun Wang together with Dr. Mridul Anjaney and Dr. Kostas Bekras from Rutgers University. We are presenting an end-to-end differentiable but explainable physics engine for Tensegrity robots. Tensegrity robots are composed of rigid rods and flexible cables, which connect together to form lightweight, deformable structures. NASA designed a space exploration rover, the SuperBall to explore the surface of Titan. While useful and versatile, Tensegrity robots are difficult to model and control. Previous work has used reinforcement learning to develop controllers for complex behaviors, such as slope climbing, using NASA's Tensegrity Robotics Toolkit as a simulator. But Sim-to-Real transfer of locomotion policy still required a lot of manual tuning of the simulator. To mitigate this reality gap, we propose a differentiable but explainable physics engine for Tensegrity robots. Benefiting from first principles, it focuses on linear models for representing contact response and actuator forces. The current work is a step towards showing data-efficient sim-to-real transfer. Where given very few examples of ground truth trajectories, it is possible to learn a good model. The engine receives the current state and control signal and predicts the next state. It computes the difference between ground truth and prediction as a loss function and back-propagates the gradient to update the system parameters. To avoid local optima and increase data efficiency, an incremental training strategy is proposed where the 5 engine parameters not related to contacts are learned first. Given only a single trajectory, the engine's prediction is very accurate. On the left is the ground truth trajectory, and on the right is the differentiable engine's prediction, which are very similar. The next step is to fix the previously learned parameters and only train the 5 contact-related parameters. Trained with only one trajectory, the engine's prediction gives a 27% relative error after 5,000 steps. The paper explores whether such an error is good enough to train controllers on the differential engine and then transfer them to the ground truth system. Both robots stop at a similar final position. This simple model is already good enough to learn a control policy for rolling the Tensegrity along a straight line. It takes orders of magnitude fewer ground truth data to train the engine instead of training the policy directly on the ground truth Mujoko system. But the policy trained in the engine is transferable to the ground truth system. They are quite similar, and a locomotion behavior is achieved in both cases. Thank you for your attention.